In this lesson, we will talk about rational and irrational numbers and how radicals are related to rational exponents. A set of numbers is said to be closed under an operation if the result of the operation on any two numbers in the set is another number in that original set. For example, if you consider the set with just the numbers 0 and 1 in it, notice that it would be closed under multiplication. Why? Because 0 times 0 is 0, which is in the set. 1 times 0 is 0, which is in the set. 0 times 1 is 0, which is also in the set. And 1 times 1 is 1, which is in the original set. Okay? So basically what this means, the reason why this set here of 0 and 1 is closed is because if I take any two of these numbers and apply the operation of multiplication to them, I am stuck getting numbers that are still in the original set, 0 and 1. So, like I said, the products 0 and 1 are both in the original set, and they represent all possible products of the original numbers in the set. Notice that the set with the elements or numbers 0, 1 in it is not closed under addition, however, because if you take 1 plus 1, you get 2. But wait a minute, 2 is not in this set. So what we say is this set is not closed under addition, because I can add 1 to itself and get a number that's not in the set. Now, finding just one counterexample, like 2 in this case, is enough to prove that a set is not closed under an operation, which is addition in this particular case. Okay, so what are rational numbers? Well, rational numbers you can think of as fractions as you know them. Or more formally, a rational number is a number that can be expressed in the form p divided by q, where p and q are integers. And if you remember, integers are the whole numbers, 0, 1, 2, 3, 4, continuing, and the negative numbers, negative 1, negative 2, negative 3. Those are all integers. Okay. So we say that a number is rational if it can be expressed in the form p over q, where p and q are integers, and q is not 0 because dividing by 0 is undefined. Another thing about rational numbers is that the decimal form of rational numbers either terminates or repeats. So for example, if you take the rational number 3 over 4, notice that this is an integer divided by another integer. Okay? Notice that the decimal expansion of this number 3/4 terminates or ends because the decimal expansion is 0.75. Also, take a look at this rational number. It's negative 5 over 6, and this the decimal expansion of this rational number actually never ends. It never ends and actually repeats. Now, as opposed to rational numbers, irrational numbers are numbers that cannot be written as fractions or as a quotient of two integers, and its decimal form is non-repeating and non-terminating. Okay. For instance, notice that the decimal form of the square root of 3, which is this, it doesn't repeat or ever terminate or end. Terminate means the same thing as end. This diagram here, this Venn diagram, shows you the relationship between the set of real numbers, all real numbers, and its subsets. You might say, why do we call these real numbers? Well, every number that you've ever worked with so far, up to Algebra 1, has been a real number. Believe it or not, there are numbers that are not real, called imaginary numbers, which you'll look at in Algebra 2. Okay. But these rational numbers and irrational numbers are just subsets or belong to the set of real numbers. Within the rational numbers, you have the integers, which include numbers like negative 5, negative 3, negative 12, and the whole numbers like 0, 8, and 154. Okay, real numbers, regardless of whether they're rational or irrational, have all of the properties with respect to addition and multiplication which you should already be familiar with. For example, the commutative property of addition says that if you have two numbers a and b and you add them in one order, it's the same as adding them in the other order, b plus a here. Also, it doesn't matter how you group addition, okay, which is known as the associative property. The additive identity just says that well, in this case, the additive identity is 0 because any number that you add to 0, you get that number back. That's why it's called the identity, because you get identically what you added to 0 back. The additive inverse of any number is the minus of that number. For example, the additive inverse of 5 would be negative 5 because 5 plus negative 5 is 0. The commutative property of multiplication just says that it doesn't really matter what order you multiply numbers in, you'll get the same result. Or for any numbers a times b, it's the same as b times a. For example, 2 times 3 is the same as 3 times 2. 10 times 5 is the same as 5 times 10, so on and so forth. The associative property of multiplication, it's similar to the associative property of addition in that it doesn't really matter in how you group multiplication. You could multiply a and b first, and then multiply by c in this case, or you can multiply b and c first, and then multiply it by a. You will get the same exact result. The multiplicative identity is similar to the additive identity, except for the multiplicative identity is 1 instead of the additive identity being 0, because notice if you multiply any number by 1, you get exactly that number back. Okay, that's why it's called the identity, because you get identically what you started with. Multiplicative inverse, once again, is very similar to the additive inverse. It says that the multiplicative inverse of a, as long as a is not 0, is 1 over a, because a times 1 over a is 1. Okay? The distributive property you're also familiar with. This is the one property that relates multiplication to addition in this way. Okay, so to reiterate, we say a set of numbers is closed under an operation if the result of the operation on any two numbers in the set, as long as the operation is defined for those two numbers, is another number in that set. To prove that a set is not closed under an operation, you only need to find one counterexample. Okay, so here are here are the real numbers, and here are some subsets of the real numbers. Okay, notice that the real numbers are closed under every single arithmetic operation. So what that means is you can add two real numbers together and you're always going to get another real number. You can subtract two real numbers and you're always going to get a real number as a result. You can multiply two real numbers, you're always going to get a real number as a result, and you can divide two real numbers, you're still going to get a real number as a result. However, if you take two irrational numbers, add them together, you are not necessarily going to get another rational number. So we say that the irrational numbers are not closed under addition. In fact, you'll notice that the irrational numbers aren't closed under any of the arithmetic operations. Whereas the rational numbers, they are closed under every single arithmetic operation, which means that if you add two rational numbers, you'll get a rational number. If you subtract two rational numbers, you'll get a rational number. We're going to work on proving a few of these facts in the next few slides. Remember, with the reflect questions, you're going to want to write these reflect questions down in your notes and come up with an answer. Come up with an answer, bring your answer to class so that we can discuss them. These are extremely important. Okay, so let's say that we want to prove that a set is closed. Alright, so given that the set of integers is closed under addition and multiplication, let's prove that the set of rational numbers is closed under addition, which means that if we add two rational numbers together, we should always get another rational number. Okay? If we can accomplish proving this, then once and for all we can say that the rational numbers are closed under addition. If you think about this intuitively, it should make sense. Think of two rational numbers in your head. If you add them together, what do you get? Another rational number. Or in other words, if you add two fractions together, what do you get? Another fraction all the time. But I can come up with as many examples as I'd like to and not have proved this fact, because I need to assume that I'm dealing with arbitrary rational numbers. And in order to do that, what I say is let a and b be some arbitrary rational numbers. Okay? Then notice that if I assume that these two numbers a and b are rational numbers, that means that a can be expressed as a quotient of two integers, and b can be expressed as a quotient of two integers. So these numbers p, q, r, and s are integers, and q and s cannot be 0 because we cannot divide by 0. Now, let's say I want to add these two rational numbers together. Notice that they don't necessarily have a common denominator here, so let's make them have a common denominator by multiplying p over q by s over s, which is just 1. So I'm not changing anything about the value of this expression here. Do the same thing over here. Multiply by q over q, which is the same as multiplying by 1, so I'm not changing anything. The reason I do that is so that these two numbers will have a common denominator in qs, because once they have this common denominator, I can just add the numerators. So in the end, what I get is that these two rational numbers, when I add them together, I get this rational number here. Okay? Because I know that ps plus qr are integers. Not only that, but I know that qs is also an integer. So if this is an integer here, this expression is an integer, this is an integer, then that means that this is a rational number. Okay, so this means that a plus b is a rational number. Okay. So what you saw before was called a direct proof. So we directly prove the fact that two rational numbers, when you add them together, you get another rational number. An indirect proof starts by assuming that what you actually want to prove is false, or not true. If the assumption leads to a contradiction, then the original statement must be true. For example, lawyers use this type of argument all the time. Let's say they're trying to prove that their client is not guilty of murder. They might say something like, okay, if my client killed this person, then that means they had to be in place A at some time, in place B at the exact same time, which clearly is impossible. So therefore, my client did not kill whoever person. Okay, it's called an indirect proof. Alright, so in this example, we're going to prove that the sum of a rational number and an irrational number is irrational. Right? So given that the set of rational numbers is closed under addition, so we're going to take it as a fact now that we've proven it, that the set of rational numbers is closed under addition, we're going to prove that the sum of a rational number and an irrational number is also an irrational number. And this is how we're going to go about it. It's a proof by contradiction, or an indirect proof. Okay? So let's let A be a rational number and let B be an irrational number. Also, let's take the sum of A and B and we're just going to call it C. And let's assume, so that we can find a contradiction, let's assume that C is irrational just for the moment. Okay, so we're basically assuming what we don't want to prove. Now notice that we can rewrite this expression A plus B equals C, which is given to us. We can rewrite this as B equals minus A plus C by adding minus A to both sides of this equation. Now, because negative A and C are both rational, they're both rational, and the set of rational numbers is closed under addition, I know that this sum must be rational. But wait a minute, this sum is equal to B. So if this sum is rational, that means B is rational. But this contradicts the condition that B is irrational in the first place, because we said in the beginning that we're going to let B be an irrational number. So the assumption that C is rational has to be false, which means that C, the sum of a rational and an irrational number, is irrational, and we're done with the proof. An indirect proof is also called a proof by contradiction. What is the contradiction in the preceding proof? Remember to have these reflect questions answered by the time you come to class. Okay, so here's a question that we answered in today's lesson. What are rational and irrational numbers? Well, a rational number, if you recall, is a number that can be written in the form P over Q, where P and Q are integers, and Q is not equal to 0 because we cannot divide by 0. An irrational number cannot be written as a ratio of integers. So what we say is, if a number cannot be written as a fraction like this, then it is irrational. The set of rationals is closed under all four arithmetic operations, while the set of irrationals is closed under none of them. Alright, so for your summary activity, this is what you're going to do. You're going to write a journal entry in which you describe how to prove a statement about real numbers by using an indirect proof.